My name's Jay Brusse. I'm a senior components engineer working for Perot Systems here at the NASA Goddard Space Flight Center in Maryland. In electronic systems, a variety of metals are ubiquitous. These include metals such as iron, copper, aluminum, nickel, just as an example. These materials are used for both structural means as well as electrical purposes for carrying current and signals. All of the metals that I've mentioned are subject to corrosion, to oxidation or other corrosive films. So to protect them against corrosion, they're usually coated with other metals to prevent oxidation. Commonly, metals such as tin, zinc, and cadmium are used for that purpose. In the case of tin or tin alloy coatings, these metals also are suitable for soldering applications. So we find tremendous amount of usage of these types of coatings in electronic systems. In the case of spaceflight systems, it's less common to find usage of zinc and cadmium coatings because they have certain properties that are undesirable in the low pressure of space. In particular, they're prone to outgassing, vapor evolution from the solid phase. However, tin coatings and tin alloy coatings are broadly used. We prefer not to use tin coatings or these coatings of tin, zinc, and cadmium because they're prone to a phenomenon known as metal whiskering. Metal whiskers are hair-like filamentary growths of metal that grow unpredictably from surfaces coated with metals such as tin, zinc, and cadmium primarily, but other metals are also prone to this phenomenon. The whiskers grow through a process of diffusion of metal atoms within the film, within the grain boundaries of that film, arriving at some nucleus on the surface. The atoms aggregate at that nucleus, begin to accumulate at the root, and sprout a crystalline metal filament as a result. The most concerning form of growth are the filamentary growths, which grow like a whisker, a human whisker, hence the term. They have uniform cross-section and can grow to substantial lengths. Finding whiskers that grow up to 1 millimeter is not very uncommon. They've been noted to grow upwards of 5 millimeters, 10 millimeters, and in the champion cases, as long as 1 inch or 25 millimeters have been reported. These are the more rare occurrences, but again, finding whiskers that can form up to 1 millimeter in length is not unheard of and not uncommon. They pose a threat to electronic circuits because as a metal, they are electrically conductive. And if they grow long enough to bridge adjacent conductors, they can produce electrical shorting hazards. The process of growth involves a timeline. There's normally an incubation period. This incubation period can last anywhere from hours, minutes, to as long as years before the first signs of growth. We don't know how to predict this dormancy or incubation period. The growth phase involves the aggregation of atoms at the root of the growing crystal, and rates of growth are also highly variable. Reports of whiskers growing upwards of 1 millimeter in length per year are somewhat common, but also slower growth rates are reported as well. Metal whiskering is not a new phenomenon. Indeed, the first reports of metal whiskers date back to just after World War II, when in 1946, a librarian working for the Aircraft Radio Corporation published the first article that we can find that reports harm to electronics from the growth of metallic whiskers. The article was entitled Cadmium Whiskers, and it detailed the discovery during World War II activities of cadmium whiskers growing from variable airspace capacitors in the radio equipment used in military avionics systems. I have an example of a variable airspace capacitor. This is about 20 years after World War II. This is a 1960s vintage air capacitor. The plates that you see here are closely spaced, a few millimeters apart. In the case of the cadmium whiskers discovered in World War II, cadmium whiskers growing in between the airspace plates produced electrical shorting hazards causing malfunction of the radios. This particular structure utilized tin coatings instead of cadmium coatings. It wasn't until after the reports of cadmium whiskers in the late 40s that people started to switch over to tin and zinc coatings as a means to alleviate the risk of cadmium whisker-induced problems. Later in the 50s, it was reported that tin coatings and zinc coatings also are prone to the formation of metallic whiskers. This particular variable airspace capacitor utilizes tin coatings around its frame, and you can easily see forests of tin whiskers growing from it. Since the early reports of metal whisker-induced harm from the Aircraft Radio Corporation in 1940s, there's been a continuation of problems due to metal whiskers throughout time. Metal whiskers have impacted electronics and avionics systems, aerospace systems, automotive industry, medical electronics industry. Essentially, no industry is immune from harm imposed by metal whiskering. A few examples of recent note include the automatic shutdown of a nuclear power plant in Connecticut back in 2005. In that case, metal whiskers growing from the tin-plated leads of a diode grew sufficiently long to bridge to an exposed printed circuit board trace that this diode was mounted to. The electrical shorting event triggered a false alarm in the health monitoring systems of that circuit. The false alarm initiated an automatic shutdown sequence of the nuclear reactor. Events like this have occurred more than once. We have reports of it occurring on numerous occasions. Metal whiskers are hair-like filamentary growths of metal that grow unpredictably from surfaces coated with metals such as tin, zinc, and cadmium primarily, but other metals are also prone to this phenomenon. The whiskers grow through a process of diffusion of metal atoms within the film, within the grain boundaries of that film, arriving at some nucleus on the surface. The atoms aggregate at that nucleus, begin to accumulate at the root, and sprout a crystalline metal filament as a result. The most concerning form of growth are the filamentary growths, which grow like a whisker, a human whisker, hence the term. They have uniform cross-section and can grow to substantial lengths. Finding whiskers that grow up to 1 millimeter is not very uncommon. They've been noted to grow upwards of 5 millimeters, 10 millimeters, and in the champion cases, as long as 1 inch or 25 millimeters have been reported. These are the more rare occurrences, but again, finding whiskers that can form up to 1 millimeter in length is not unheard of and not uncommon. They pose a threat to electronic circuits because, as a metal, they are electrically conductive. And if they grow long enough to bridge adjacent conductors, they can produce electrical shorting hazards. The risks posed by a metallic whisker fall under two primary categories. The first is electrical shorting hazard, and the second has to do with debris hazard or contamination hazard. This latter hazard of contamination or debris becomes more of a concern as electronics start to integrate the use of micro-electromechanical structures, very miniaturized moving components where something the size of a metallic whisker could impede the function of the device. However, for the time being, the real dominant concern is clearly electrical shorting hazard. A metallic whisker is an electrical conductor. It has an electrical resistance associated with it. The resistance is a function of its length and its cross-sectional area, as well as the resistivity of the material in question. If a whisker bridges a pair of electrical conductors that are at different electrical potentials, there is a risk of an electrical short occurring. The short can be an intermittent short if the current flowing through the whisker is sufficient to raise its temperature above melting, much like an electrical fuse filament would work in any kind of electronic assembly. If the current rises above its rating, it fuses open and current flow ceases. In this case, we would have an intermittent contact, an intermittent electrical short. It may not be perceived by the system. It depends on the sensitivity of the circuitry to a brief momentary current flow, a shorting event. If, however, the electrical current that's flowing through the whisker is lower than the current required to raise it to melting temperature, then a permanent short can result. Once again, the sensitivity of the circuitry to having a physical bridge of this kind varies from application to application. Many systems may not notice an electrical short of this nature, but others can be catastrophically disabled as a result. A third phenomenon is known as metal vapor arcing. This is a much more concerning phenomenon and can produce very serious damage. In the case of metal vapor arcing, when the whisker bridges to the adjacent conductor, if there is sufficient amount of current during the shorting event not only to raise the temperature to melting, but to continue to raise that temperature to the boiling point of the metal, the whisker can vaporize into a metal gas. If the voltage is high enough across that metal gas, the gas can be ionized into a metal plasma. This plasma can be struck into an enduring arc if there's sufficient voltage and current available across this plume to continue to boil off fresh metal from the source surfaces, the surfaces where the whisker is growing from, and or the surface that the whisker has shorted across to. The arc can get sufficiently hot to continue to feed more material into this growing plasma, and currents have been sustained in excess of hundreds of amperes, where nominally a typical tin whisker may only be able to sustain a few tens of milliamperes of current flow. In the case of a metal vapor arc, the metal plasma is able to sustain hundreds of amperes and can destroy electronic systems. If whiskers are dislodged from the surface they're growing on, they can be redistributed around within an electronics assembly and pose a risk of shorting as loose object conductive debris. This phenomenon is responsible for massive failures in computer data centers, where the raised floor tiles utilized in these rooms make use of a steel underpanel that is zinc coated. The raised floor tiles can grow forests of whiskers by the hundreds of millions in a given data center. When operations in the room require the lifting of these tiles to do work under the floor, it's possible to dislodge these whiskers from the floor tiles by the millions, if not greater numbers, and have these whiskers be redistributed by the air conditioning systems and drawn directly into the critical electronic systems operating above the floor. Numerous data centers around the world have reported massive failures as a result of loose object debris from metal whiskers, as a result of whiskers dislodged from floor structures commonly used in this environment. After the reports by the Aircraft Radio Corporation of cadmium whiskers growing from cadmium-coated structures, the industry began to convert over to alternative coatings. Among the alternative coatings were tin and zinc coatings. In the early 50s, Bell Laboratories reported that these films also are prone to grow whiskers unpredictably. And in the early 50s, Bell Laboratories began an exhaustive effort to find out what additives can be co-deposited with tin coatings to help quench the phenomenon of metal whisker growth. They spent more than a decade experimenting with a variety of metals that can be easily co-deposited with tin. They found that co-depositing lead at a level of about 1% by weight was sufficient to dramatically quench the formation of metal whiskers. By quenching, I mean the density of growths was reduced, as well as any whiskers that do grow, they tended to only grow to a few mils, a few thousandths of an inch in length, and have no subsequent growth thereafter. Such short whiskers are generally not a nuisance to electronic systems. Unfortunately, similar research was not carried out to find out what, if anything, can be added to zinc and or cadmium coatings to quench whiskering. In the 1990s, the U.S. military began to alter their procurement documents for electronic components to prohibit the use of high-purity tin coatings. The primary requirement now stipulates that any use of tin coatings in electronic componentry must be coupled with lead as an alloying constituent, and the ratios vary from one procurement document to the next, but nominally 3% lead by weight is quoted as a requirement for tin-based coatings in military and aerospace components. The work done by Bell Labs throughout the 1950s and into the 1960s helped to identify lead as a useful alloying constituent with tin coatings to inhibit whiskering. Since that time, NASA and other industries have made very successful use of tin-lead surface finishes without the threat of dramatic whisker-induced harm. However, beginning around the year 2000, international legislative groups began to promote laws that would forbid the use of lead within electronic systems. In particular, they're targeting consumer electronics, citing lead as a hazardous material to humans. As these legislative measures began to take effect, the electronic component industry began to seek out alternative coatings to tin lead so that they could continue to sell products into regions that have prohibitions against lead in those devices. The most prominent choice, the easiest transition for these suppliers, was to eliminate the use of lead in their tin lead systems, and as such migrate back towards pure tin coatings. So we see a conflict here that the international laws are pushing for a restriction on the use of lead, whereby here within the United States there currently does not exist any similar federal legislation. So aerospace organizations like NASA continue to push for the use of leaded tin coatings as a means of building reliable hardware against the threat of tin whiskering. We're finding it more and more difficult to obtain components that bear lead. Our command of the marketplace, our market share for the electronic components is very small. As such, the supply industry is catering to their primary constituents, their primary market, their primary customers, who are subject to the legislation of not allowing the use of lead in their electronics. The primary threat posed by metal whiskers is electrical shorting. The first thing to try to do is to avoid the growth of whiskers. For that purpose, we recommend not using metals that are prone to growth of whiskers. And by that I mean we generally prohibit the use of high purity tin coatings unless they're alloyed with lead as the primary alloying constituent. The use of other metals as an alloying constituent is less broadly studied, and we don't have sufficient data to recommend tin plus some other alloying constituent as a reasonable mitigation strategy at this time. Similarly, we recommend avoidance of zinc and cadmium coatings for the same reason. If your system cannot tolerate the growth of whiskers, the best course of action would be to avoid the use of metals that are prone to growth of whiskers. We understand that avoidance is not always possible, so we can turn to alternate mitigation strategies to reduce our threat from harm. Again, the primary hazard posed by metal whiskers is electrical shorting. If one can produce an insulating barrier that can prevent the whisker from making electrical contact to an adjacent conductor, then we've reduced the threat of harm. For this purpose, the use of conformal coating is one mitigation strategy that we broadly recommend and make use of. Conformal coats come in a variety of forms, variety of material structures: polyurethanes, silicones, acrylics, paralenes, to name a few. Conformal coat presents a potential risk mitigator by in three ways. The first way is when applied on top of a whisker-prone surface, we question, will that coating somehow prevent whiskers from growing in the first place? In research that we've done at the Goddard Space Flight Center with polyurethane coatings, we found that the polyurethane coatings do not prevent the nucleation and subsequent growth of whiskers. They do, however, provide a barrier to elongation of the whisker. When applied on top of the surface, the whisker, as it grows, will need to lift the coating or raise it or puncture it in some fashion. What we've seen with the polyurethane coatings that Goddard uses is the whisker as it begins to grow, begins to lift the coating so that it loses its adhesion to the surface that it's applied to. In doing so, it begins to raise the coating as if raising a circus tent. As the whisker continues to elongate, it begins to cause separation, a broader separation zone of the coating to the surface that it's applied to. Whiskers, as they grow longer, are subject to a phenomenon known as Euler buckling. Euler buckling is a measure of the whisker's strength under a compressive load. So as the whisker gets longer and longer, its Euler buckling strength gets reduced. If we think of a metal whisker filament as a structural element, much like a column or a beam used to sustain a compressive load in an architectural structure, the shape of that beam, in terms of its cross-sectional area and its length, are important factors in judging its ability to sustain greater and greater loads. A column, as it gets longer, its strength under compression is reduced by a factor of 1 over its length squared. Similarly, its strength is directly proportional to its cross-sectional area raised to the 4th power. This is for a circular cross-section beam or column. I commented that whiskers, as they grow, do not normally change their cross-sectional area. Rather, they grow very rapidly in their growth axis compared to the opposing axes. So the cross-section stays uniform as it elongates. Since the strength of the whisker is proportional to 1 over its length squared, as it gets longer, its strength under buckling forces, buckling loads, gets reduced. What we've seen with the polyurethane coatings that we've been experimenting with at Goddard is when applied to a thickness of a couple of mils, 0.02 of an inch, the whiskers at first, because they're short, their aspect ratio length to width is low, they're very stiff and they're able to begin to lift the coating. However, as they elongate, their buckling strength decreases, and we see the whiskers grow up to a certain amount and then curl over within the coating, never being able to puncture their way through. The effectiveness of the conformal coating materials, different conformal coating materials, will vary. The comments I've made are specific to one particular polyurethane formulation that's popular here in the aerospace industry. Folks have experimented with parylene coatings and other coatings and find similar behaviors, but they also have observed the cases where whiskers are able to puncture the coating because the material's self-cohesion is not high enough. Puncture the coating because the coating material's self-cohesion is low, and as the whisker lifts the coating begins to tear. The third way in which conformal coat can provide protection against whisker-induced harm is when the coating is applied to the adjacent surface from which the whisker is growing. As the whisker grows and reaches over to that adjacent conductor, if there's an insulating film applied to it, polyurethane coating for example, the tip of that whisker will have to depress and burrow into that coating in order to make electrical contact to the conductor below. What we find again is a calculation of the Euler buckling strength of that whisker as it's elongated, trying to push into the coating. When we compare the Euler buckling strength of an elongated whisker versus the displacement of that coating, the toughness of that coating versus a load that's trying to compress it, normally we find that the coating wins out, that the whiskers generally don't have enough strength to be able to repenetrate the adjacent coated surface. A third strategy to reduce threat of harm from whiskers is to replace whisker-prone surfaces upon receipt of the item. One method for tin coatings is to remove the tin coating surface by a process of dipping the component into a solder pot of molten solder. For this purpose, we'd recommend the use of a leaded tin solder, such that once you dip the component into the solder pot and remove it, you've replaced the original tin finish with a tin lead finish, which is far less prone to growing whiskers. This practice is not suitable for all kinds of components, but is for solderable components and surfaces that are normally used in solder joints. This is a viable mitigation strategy, as long as one ensures that the process that they use for dipping does not induce other damage to the component.